So what we're going to be looking at now is we're going to be looking at what's called proof by cases. And so when we do proof by cases, what we're going to do is we want to determine the method for proof that you want to use in order to prove a statement, okay, first, and then you want to determine which cases you must use to fully prove by cases, or to prove the proof by cases. We use proof by cases because it's powerful for it to use if there are a limited number of options for our variables, and a single proof for all members of our domain is impossible, okay? And so what we really want to think about is we want to think to ourselves, okay, well, if I broke up this particular proof that I'm looking at into a couple of sets of cases, is it going to be easier than if I prove it for all of them? Or is it the case that it may not even be possible for me to prove a statement for all possible cases, or excuse me, for all variables unless I break it up by cases, okay? So let's take a look at some problems, because I think that'll maybe help us to understand when it is that we're going to use proof by cases. So let's take this example. Let's say, for example, integers x and y. If xy is odd, then x is odd and y is odd. That's what we're going to try and prove. So let's actually say to ourselves, okay, well, what are the different cases that we could possibly have here? In this case, we could have x is odd, okay, and y is odd. That's one option. We could have x is even and y is odd. We could have x is odd and y is even. And we could have x is even and y is even. So in this case, there's only a limited number of examples that we could possibly have, or a limited number of choices or cases that we could have in this situation. But what you want to notice is that for this statement to be true, we need both of these to be true. X is odd and y is odd. So what we really want is we want to make sure that, well, x is not even, right? And we also need to make sure that y is not even. So those are going to be the things that we assume. Let's assume that y is even, right? And then what we're going to do is we're going to induce some kind of contradiction, right? We're going to show that it's going to be impossible, that xy would not in fact be odd, all right? And so if you kind of think about that, if we show that x can't be even and we show that y can't be even, that means that x must be odd and y must be odd, all right? So we're going to use two proofs, right, in order to prove this statement about these two statements about x and y being odd, okay? So let's say, for example, our case 1 is going to say x is even and an integer. So we'll use that as case 1. And 2 is y is even and an integer. So what that does is if I show that both of those cannot be true, then what I end up with is that only x is odd and y is odd. Okay? And both should be fairly easy, right? Or not incredibly hard. So we'll start out with x is even. So we know that means that x is equal to 2k for k belonging to the integers. Okay? Then what we get is that xy is going to equal 2ky, right? Which for some k, right, our k belonging to z, so xy equals 2 times ky, and so xy is odd. Xy is even. But that's impossible because we were told at the beginning that xy is odd. But since xy is odd, x cannot be even by contradiction. So x is odd. So x must be odd. 2, we're going to get a very similar proof. We're going to let y equal 2j for j belonging to the integers. Then we get that xy equals x times 2j, which equals, and we can rewrite this as 2 times xj. And so xy, again, is even. But by assumption, x was odd. xy, was odd. So that means by contradiction, y must be odd. And that exhausts all of our cases. Therefore, if xy is odd, then x must be odd and y must be odd. So when I look at this in terms of proof by cases, okay, what I can see is I can see that if I choose the right cases, that I'm going to end up actually negating all the ones that I do not want, and I'll be left with the one that I do want in this case. All right, and this is especially easy when we're dealing with even and odd problems, where we want to make sure that two of our variables must be of a certain kind, because there are only so many choices that we can have. If we have two variables, there are only 4 choices that we can have. And if we're smart about the way that we make those choices, then we kind of eliminate everything that we don't want, and we can only need to prove the cases that we need to. Okay? So in this case, we can see, right, if I want to say that xy is odd, right, then by proving that x is not even and y cannot be even, then we show that x and y must both be odd. So let's take a look at another example. Let's say, for example, we want to show this thing called the triangle inequality. It's super famous in math and really, really handy. Okay? So for all real numbers, x and y, the absolute value of x plus y is going to be less than or equal to the absolute value of x plus the absolute value of y. Now, the one thing about absolute value problems is that what we know is there's only a limited number of cases. Okay? There's only a limited number of cases that we could possibly have. So one way that we might say this is we might say, okay, well, let's think about what those possible cases might be. All right? So first, for the absolute value of x plus y, okay, that could equal negative x plus y, or it could equal just x plus y. Okay? So we've got x plus y or negative x plus y. In the case of absolute value of x, right, the absolute value of x could equal negative x, or the absolute value of x could equal x. Okay? And we could also have that the absolute value of y could equal negative y, or the absolute value of y could equal y. Okay? In any case, what we'll end up getting is we're going to end up, and if you think about this, this makes some sense, we're going to get that the absolute value of x, okay, is always going to be, well, x, the value x, is always going to be less than or equal to its absolute value, and negative x is always going to be less than or equal to its absolute value, right? And the same can be said with in the case of y, and the same can be said in the case of x plus y. And if you just think about it, if x happens to be negative, right, then x is going to be less than or equal to the absolute value of x. And if x happens to be positive, then negative x is going to be less than or equal to the absolute value of x. So that kind of makes some sense. So I've got a set of cases here that I can kind of think through that maybe will help me prove this particular problem. So let's go here and let's work with these ones. Let's start with these two statements because they're on the left-hand side and we can actually use them to kind of fully prove our statement. So we'll start with first that the absolute value of x plus y, okay, is equal to, right, negative x plus y. Okay? Right? And in that case, that's actually, we might say this case of x plus y is less than 0. Right? So if that's the case, then the absolute value of x plus y is equal to negative of x plus y, which equals negative x plus negative y. Okay? And we actually said that this is then going to be less than or equal to the absolute value of x plus the absolute value of y. Right? Because each one of these individually is less than these two individually. Or less than or equal to them individually. So that's done. Okay? We've in fact shown that this absolute value statement is less than this one. or excuse me, yes, exactly, is less than that one. Now 2, we could have that x plus y is greater than 0. And in that case, we have this second piece here, that the absolute value of x plus y equals x plus y. So we'll take that, we're going to take the absolute value of x plus y, okay, is equal to x plus y. And we already established that if it is the case that x is less than or equal to its absolute value each and every time, so this is going to be less than or equal to the absolute value of x plus the absolute value of y. And so now, if that's the case, right, that it's greater than 0, then we're done. Now, by the way, I could actually add a less than or equal to 0, because then x plus y would equal its absolute value, so we might as well just utilize the equal to sign there as well. Okay? So, what that tells me is, basically, our end result here is if x plus y is less than 0, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And if x plus y is greater than 0, then the absolute value of x plus y is greater than or equal to 0, excuse me, is less than or equal to the absolute value of x plus the absolute value of y. Well, we've exhausted our cases. So the absolute value of x plus y is going to be less than or equal to the absolute value of x plus the absolute value of y. And we are done. Okay? And so this is another example. Absolute values are a really good example of when we should be using proof by cases, because basically all we have is we have a negative and we have a positive. And that pretty much exhausts all the different ways that we can get an absolute value. All right? So this completes my explanation of the proof by cases.